Hello AP Chemistry and welcome to 16.10, which, oh my goodness, it's the last section of chapter 16. Though there are still a whole bunch of 17 lectures to go. But you know what? We will celebrate this this little milestone. Anyway, 16.10 is all about structure, which means that 1, you need to be comfortable with your Lewis structures. 2, in the ideal scenario, you can envision the Lewis structures, right? Like you can see it in your head when you look at the formula on the paper, right? That's the ideal scenario. Not everybody's heads work that way, and that's fine. If it doesn't, you need to be able to quickly doodle out a Lewis structure as needed, so that way you can make sense of what's being asked of you, right? So anyway, going back to your guys' notes, right? The factors to consider if we are gauging the strength of an acid, right, is to determine the polarization of that HX. And note that X can be an atom or it can be a series of atoms, right? It's just the polarization of that bond between the hydrogen and the rest of the molecule, right? The bond strength of that hydrogen to the rest of the molecule, right? And the stability of the resulting conjugate base, okay? Do be mindful here, right, that what it means, all of this is just about the ease with which that hydrogen can be taken away by a water molecule, right? Because that's what it means to be an acid, right? It's the ability to lose that proton, right? So that's what we're looking at here. So for binary acids, right, this is that figure from your guys' group, from your guys' book, right? As we go down a group for a binary acid, and when we say binary, we mean, right, it's only composed of 2 elements, right? Just to make sure we're all on the same page here. It's only composed of 2 elements. So acid strength increases this way, right? And the primary factor here is going to be your bond strength, right? And if we think about the hydrohalide series, right, that's a good one to look at, right? In that, HF has the strongest bond, right? That HF bond is the strongest bond because, right, they are the 2 smallest atoms, right? Which means that they're able to get very close together, right? Which means that there is a strong force of attraction between those 2, which means that that fluoride does not readily let go of, right, that hydrogen, right? Which is why that is an exception to our strong acids, right? And often that, trick question that shows up on, say, like a multiple choice, right? When we're talking about a period trend, acid strength tends to increase, right, as bond polarity increases. And bond polarity, especially for a binary series, just has to do with, right, electronegativity, right? As the electronegativity increases, going in this direction, right? As the electronegativity increases, that bond gets more and more polar, and we end up with stronger and stronger acid, right? Especially if we were to compare like this series right here, right? As we move over, right, they get more and more acidic. Yes, makes sense. And so that's all we're doing. So really to analyze a binary acid, really we're just going to go take a gander at the periodic table, right? And see are they in the same group or the same period, right? If they're binary acids anyway, right? And then make that distinction. Okay. If we're looking at oxyacid series, right, which means that we're starting from a polyatomic ion, right, and then there's a hydrogen attached, please always remember that that hydrogen is always going to be attached to an oxygen, yes? As in you should envision polyatomic ion, and then go ahead and attach an H to one of the oxygens, right? So there are 2 different ways to analyze our oxyacids, right? If we're given a series of oxyacids like here, let me get a darker color. Like here, right, we're just looking at an oxygen bonded to a hydrogen, and that oxygen is bonded to that Y, right? So really, so when they say OH, that's what they're saying. We are just looking at the electronegativity of Y, right? The more that Y atom is able to pull electron density towards itself, which means pulling it away from this OH bond, right? The more readily that hydrogen can be taken away by a water molecule, right? Which is why this one with the highest electronegativity is also the most acidic, right? Going to a series of oxyacids, right? So here we have a series where these are all the same nonmetal, right? Or the same basic part or the same central part, same central atom of our polyatomic ion, and all we're doing is increasing the number of oxygens. Oxygen is relatively electronegative, right? Especially if we look at its oxygen is right here, right? If we look at the proximity of oxygen to fluorine, right? Very electronegative, right? So The more oxygens that polyatomic ion has, the more electron density is pulled away from that hydrogen, the more readily that hydrogen is lost, right? That oxygen also allows for the option of resonance structures, right? Which means that we end up with a more stable conjugate base after it has been deprotonated, right? So for all those reasons, if we're comparing a series of oxyacids with the same central atom, then the more oxygens there are, the stronger the acid, okay? So if we were tasked with determining which is the most acidic given a series, we would look at those things, right? So if we're looking at HBr versus HF, right, bromine and fluorine are in the same group. So we would be looking at, like we said over here, we'd be looking at bond strength, right? HF has a stronger bond than HBr, looking for more acidic. So the one that will more readily lose its proton is HBr, right? pH 3 or H2S, again, we're looking at some binary acids, right? Phosphorus and sulfur are in the same period, right? So then we are just looking at which is the more electronegative, because the more electronegative means a more polar bond, which means a stronger acid, right? Which is going to be this one. So again, more electronegative element, more electron density is pulled away, right? More polar bond, right? And the better that hydrogen is able to be taken away. Here we have, this is that series of oxyacids, right? In that we have a nitrogen at the center, right? And that nitrogen here is attached to 2 oxygens versus 3 oxygens, right? 3 oxygens means more electron density pulled away from the hydrogen, more resulting stability for that anion, right? This is the more acidic of the species, right? Here we have 2 oxyanions, right? But we'll note that they both have 3 oxygens, so that's not what the question's about. It's really about this element right here. So now, right, since we have equal number of oxygens, we just need to know which is more electronegative, the sulfur or the selenium, right? Sulfur versus selenium. Sulfur is more electronegative, right? So this then would be the more acidic species. Yes, does that make sense? All right, so, you need your periodic table. Make sure this makes sense. Come see me soon if it doesn't. All right, thank you for listening. Be good, and I will